Hey, chemistry, how you doing? Welcome to your first flipped lecture that has to do with actual chemistry. The last lecture that you watched had more to do with what does it mean to be a Christian doing science, and that is uber important. I hope you learned a lot from it, but we're now going to jump into chemistry proper, the study of matter and how it reacts with itself. We are here looking at the nature of matter and energy, which is the fundamental nature of the cosmos. What is this universe made out of? And how can we study it? Okay, matter is anything that has mass and volume. Anything that on Earth here would move a scale. Anything that has mass and takes up space is matter. So pretty much everything. Everything is matter, unless it's some form of energy. And so we have some terms that we use to describe matter. If something is a pure substance, meaning that it is made up of only one kind of atom, then we call that pure substance an element. So here's an example. My ring is made out of titanium. And so titanium is an element. And except for the paint on the outside of this ring, it's a titanium ring, and every atom in this ring is titanium. It's exactly the same. You could cut it apart and look at it in the smallest piece that you wanted to, and you would still find only one kind of atom, right? And that is that's an example of an element. Other examples might be like gold or silver or oxygen or nitrogen or hydrogen. There's a lot of them. And any element is a pure substance made up of only one kind of atom. Now, what happens if it's not a pure substance? What happens if it's like my coffee mug that was given to me by chemistry students a couple of years ago? This is stainless steel. It's mostly iron, but it actually has some other elements in there, including carbon and usually some magnesium and things like that. But this is not a pure substance. If I were to cut this into itsy bitsy pieces and look at it under some really powerful tunneling electron microscope, I would see that there's actually more than one kind of atom in here. And so we call a substance made up of more than one kind of atom a compound. And the smallest unit of a compound is a molecule. Now, if you were to cut up a molecule into its individual atoms, now you'd be back to elements, right? So multiple atoms together make up an element, sorry, a compound. And a compound is represented by repeating units of that molecule. All right, let's move on. Here's an example of an atom. So an atom, as you already know, is the smallest unit of an element. It is the smallest fundamental unit of matter. Now, you can break an atom up as this picture shows, but typically we think of atoms as the fundamental unit of matter. And they have a positively charged nucleus that is surrounded by a negatively charged electron cloud. So this picture that you're looking at here, this is a model of the atom that is fairly accurate. It's called the planetary model because it looks like there's a sun and planets orbiting it. And this is a good way to think of an atom. But remember, this is a model. So it's not an absolutely true picture. We're going to see some better pictures in a minute, and I'm sure that there's even better pictures that can be drawn that we haven't figured out how to draw yet. But this is a good, workable model of the atom. The atom is composed of a nucleus that has protons and neutrons in it, and the neutrons are neutrally charged, hence their name, and the protons are positively charged. So the nucleus as a whole has a net positive charge, and the nucleus is where all the matter, all the mass of the atom is. But then there's this larger volume that the atom takes up, and it's made up of itsy bitsy teeny tiny electrons that are negatively charged and are zipping around the atom at very near the speed of light. And so the itsy bitsy electrons, and they're a lot smaller versus protons and neutrons than this picture is, but it's there just to help you conceptualize it. These electrons exist in layers, outside of the nucleus, and we're going to get more into electron orbitals and all that kind of stuff later on. But for right now, this is the concept you need to have. Okay. Here's another model of the atom. This is better because the electrons are orbiting not in one plane. Here it looks like they're all sitting in a solar system disk. That's why it's called the planetary model. This helps you understand that they orbit in lots of different directions. But even this is not really the best picture we have. This is better, where electrons aren't even ellipses at all. Most of them are not circular. Most of them are kind of like Q-tip shaped, which is a little strange. And they come out at all different angles from the atom. So again, this is an example of models improving over time. This is an even better model of the atom that shows that some orbits are actually like donut shaped around the nucleus. It's crazy. But then we get these atoms, and now I'm representing atoms as simple little balls, right? But we get these atoms and we join them together and we form chemical bonds between them, and we call this a molecule. Now this happens to represent the water molecule, where I have 2 hydrogens and an oxygen. But again, this is a model. Bonds are not actually sticks, right? And atoms are not actually balls. This is just one way of representing. This is one model of a molecule, but you can see the concept here, right? A molecule is a collection of different kinds of atoms chemically joined together. And if you have a whole bunch of these water molecules, you have a drop of water. Okay. Molecules get more complex though. Here's another model of a molecule with lots of different kinds of atoms on it. And they've used color coding to help us identify what kind of atom is the same as another. And they've even used double bonds and single bonds. And this is crazy, and you're going to get into this later on in your book too. But models help us understand the way that matter is made up. Okay? So chemists use a shorthand to indicate which elements are present in a substance. And so we might talk about sugar. And just a spoonful of sugar helps the medicine go down. Right, that was free. We could say the word sugar, but a chemist doesn't know what sugar is based on its spelling of the pronunciation. That doesn't help us understand what sugar is. So we use a shorthand to represent sugar. And we might build a model of it. This would be a model of sugar like we've seen before, where we have colored balls representing different kinds of atoms. In this case, all of these gray ones are carbons, and these are hydrogens, and these red ones are oxygens. And this model helps us understand it, but it's kind of laborious to write that down all the time. If you're talking about sugar, now I have to draw this all the time. So chemists use a shorthand. It's called a formula. And this is an example of a formula for sugar. And what this represents is we use letters to tell what kind of atoms we're talking about, right? This C represents carbon, the H represents hydrogen, the O represents oxygen. And we did a little bit of work with the periodic table a couple of years ago in physical science, and hopefully you remember what some of these elements' shorthands are. If not, you'll get it again. We're going to spend a lot of time doing this, so you'll understand the elements and their shorthand. It'll be something that comes to you pretty quickly. Okay, so that's the letters in a formula. Now we also have numbers, right? The subscripts indicate how many of that atom. So when it says C6, that means 6 carbons. H12 means 12 hydrogens. O6 means 6 oxygens. All right, so this is another way of writing down what sugar is. If we just say the word sugar, you don't know what it is. But if I write down C6H12O6, now you know. And especially if I were to draw a model or a picture of it, then you're like, oh, I know how all that's bonded now too. In compounds, you have multiple kinds of atoms that are chemically joined together. And these units get repeated a whole bunch of times to make up a pile of this compound, right? Sugar, salt, something like that. But in a mixture, we have also multiple kinds of atoms, but they're not chemically bound to each other. They're just sitting there like good little neighbors. And they're mixed around, and they're not necessarily repeating in the same units as you look through the mixture. It's somewhat random, somewhat chaotic, and you've got things just sitting there. Not joined, just sitting there. So we call that a mixture. And it could be different kinds of atoms sitting next to each other, or it could be actually multiple kinds of molecules sitting next to each other, not chemically bound. And so we call that a mixture. And you're familiar with this term all the time. I'm going to stick a little bit of more terminology in front of it and introduce you to 2 kinds of mixture. One of them is a homogeneous mixture. Homogeneous means all the same, uniform, smooth, right? So a homogeneous population might be a group of people that are all the same ethnicity, relatively close to the same income level, and might all be relatively the same age. And a really homogeneous population might all be the same gender, right? Homogeneous means all the same. In a homogeneous mixture, all of these units that are sitting next to each other and not chemically joined are dispersed evenly, so that if I sample the mixture and I look at it really carefully, I find that it's arranged the same way as another sample. Another way of thinking of a homogeneous mixture is that it's dissolved in itself. Something is dissolving something else. And so the things that are dissolved are surrounded by things that are dissolving it. So if I mix salt with water and I stir it up, the salt goes into solution. That's a homogeneous mixture. Everywhere I grab a sample of the solution to take a look at it, I see water surrounding salt ions, right? Another way of thinking of homogeneous mixture would be something that when you look at it, you see only one phase. Now, one phase, what does that mean? That means that you only see one thing, one stage, one layer. You don't see blotchiness, splotchiness. You don't see things settling out, right? A homogeneous mixture is smooth. It's uniform. It's not chemically bound, but it is dissolved. And we'll get into more what solutions are in a little bit. But for right now, that's a homogeneous mixture. Now, it's different than a heterogeneous mixture or a heterogeneous mixture. In a heterogeneous mixture, you have at least two phases, which means you've got layers. So I could take water and I could take oil, and I can put them in the same beaker, and I could stir, 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 stir. And when I did, it would mix up, but I'd see blotchiness immediately. And if I let it sit, I'd see layers, right? And so it's still a mixture, but it's a heterogeneous mixture. It's not smooth. It's not uniform. If I sample one place and then I sample another place and I look at it, they're not the same. And so that's a heterogeneous or a heterogeneous mixture. Okay, let me show you some pictures. Here we have some examples of things that are dissolved. This would be a homogeneous mixture, right? Here I have some kind of solute, and you'll get to know that term in a minute, some kind of thing that is dissolved, and I have some kind of solvent, some kind of thing doing the dissolving that's surrounding it, and they're all mixed up. Here's another picture, just bigger solvent particles surrounding the same kind of solute. So here we have something dissolved, and if I sample this, I get green and yellow all mixed up. If I sample that one, I get green and blue and yellow all mixed up, right? They're smooth, they're uniform. If this weren't a magnified image of molecules, and I were to step back and look at it, it might look completely uniform, right? This, on the other hand, this is a heterogeneous mixture. Here's a bunch of different colors of peas in a bowl. Nobody has dissolved anybody. It's not a uniform. If I were to sample right here, I'd get black and some tan. If I were to sample over here, I'd get red and some black. Sample over here, I get white, just a little bit of red. So not uniform, not the same. And you see chunkiness, okay? That's a heterogeneous mixture. Looking at solutions, this is one of my favorite things in the universe. This is chocolate cake batter. Praise Jesus for chocolate cake batter, okay? This is a homogeneous mixture. And so here I have smooth, uniform. The lovely pieces of chocolate are surrounded by lovely amounts of milk and oil, and I want some right now. And that's uniform. If I sample that, then I will find the same sorts of things no matter where I sample it. These are examples of solutions as well. Sugar and salt, one phase. I look and I see one thing. This is dissolved. This is homogeneous. Sand, no, I see chunkiness and I see layers. So it's a mixture, but it's a heterogeneous mixture. Okay? Tap water is a mixture versus distilled water, which would be a compound, right? This is all one kind of molecule repeated over and over and over again. And so this is just the compound water. But here I have water dissolving other things, different kinds of minerals and ions. And so that's actually a homogeneous mixture. Okay? Hope that makes sense to you. The next thing we're looking at are different kinds of change. So your book talks about physical changes versus chemical changes. Physical changes do not affect chemical bonds. They don't affect the chemical makeup of a substance. If I take water, a water molecule, and I get it really cold, it's going to freeze together with its friends and form a crystal lattice, right? But it's still water. If I heat that ice up, it's going to melt. If I heat it up even more, it's going to boil. And it's going to become steam, and it's going to change its physical properties, but not its chemical makeup. That's an example of a physical change. But if I take carbon and I add oxygen to it under the right conditions, now carbon and oxygen form chemical bonds, and I get carbon dioxide. That's a chemical change. It's no longer just carbon and just oxygen. Now they've joined together and they've made carbon dioxide. And that's a chemical change. So physical changes do not rearrange chemical bonds. Chemical changes do. And so that's one distinction you need to have in your mind. And we'll do a lab about that this week. Okay? The law of conservation of matter. This is another big concept. You can't make or destroy matter. Sorry, only one thing can do that. His name is God, right? We in the dominion he's given us don't have that power, and the science that we have can't do it. We can't take a substance and destroy it, annihilate it. We can't take nothing and make something out of it. So the law of conservation of matter says that matter can be changed, but never created or destroyed. In all the chemical labs we're going to do, we're going to take matter and we're going to react it with more matter, and there will be energy released or absorbed, but no matter and no energy will ever be created or destroyed. The same thing is true with energy, right? Energy is the ability to do work. You talked about that in physical science. You'll spend chapters on that in physics coming up next year. But right now for chemistry, we're going to be looking at the energy available to make or break bonds. And no matter what kind of chemistry you do, no matter how hot or cold something gets, it is not making energy. It's simply changing energy's form, right? And so the first law of thermodynamics talks about the conservation of matter and energy, that no matter and no energy can be created or destroyed. It just changes form. That's all the chemistry can do, is rearrange things and change it from one form to another, but not make it and not destroy it. So some forms of energy. Physical science, again, you already talked about this. We actually spent a long time on this in physical science. There are different forms of energy, and there's a lot more than just these four. But just to kind of jog your memory, there's kinetic energy, the energy of motion. There's potential energy, where something is sitting on a ledge and could fall, and there's potential energy in its position. There's thermal energy, the energy of heat. Again, my nice hot tea. Thank you, former students. Energy of heat is thermal energy. There's chemical energy like gasoline and explosives, where in the chemical bonds is a lot of energy that can be released and it goes boom, right? That's also what's in sugar. That's why you eat your food. So there's more and more and more kinds of energy in your book. We'll go through a big long list of them, but in this I just want to jog your memory and have you go, oh yeah, different kinds of energy, right? The second law of thermodynamics, and again, chapters on this in physics, is that in any given system, energy flows from higher levels of energy to lower levels of energy. So in your chemistry, you're going to always be spreading energy out. You're going to take energy from some high energy source and you're going to use it to do work, and it's going to go from a source of high energy to a source of low energy. You've got a Bunsen burner with lots of chemical energy, and you're burning that chemical energy and making thermal energy out of it. And the thermal energy heats up the beaker, heats up the water, heats up the things in the water, lets a chemical reaction happen, and the energy always flows from a source of heat to a source of, it's bad wording, not a source of cold, to a place where there isn't as much heat. And so energy always flows downhill, and that's something that you'll have to keep in mind. And we'll play with this a lot in chemistry. You played with it a lot in physical science too. So all of this just big picture lecturing from 20,000 feet, right? Just as an image to remind you of this, here's the sun, which gets the earth warmer, and then the moon gets some heat from the sun and also gets some reflected heat off of the earth, and the energy flows from here to here, right? It doesn't, the moon never warms up the sun. That's not ever going to happen, okay? Last concept is in chemical reactions, where we're talking about energy and heat, there's basically two kinds of chemical reactions. There's a chemical reaction that absorbs heat, and there's a chemical reaction that gives off heat. So if something gives off heat, we call it exothermic. You see the word heat in here, right? Thermos, thermic, that means heat. Exo means out of, like, exit, extraterrestrial, right? Exo, outside of. This is heat leaving, exothermic. Endo means inside. Endoscope, endoscopy, endometrium, endo words coming into my mind. Endo means inside of something. So this is heat that's gone in. So this is a chemical reaction that absorbs heat. Just a quick example. This is a bonfire, and here we have lots of chemical energy being released in the form of fire. I love fire. And fire gives off heat. So this is an exothermic reaction. This is an example of an endothermic reaction. In an endothermic reaction, chemicals are reacting with each other and they need heat from their environment to make that reaction happen. So everything around them gets colder because they're sucking the heat out of it. So that's the way the ice pack there works, is the ice pack is a chemical reaction that when it progresses, it absorbs heat from its environment to make the reaction happen. And that means that your hand gets cold. So it helps your boo-boo. There you go. If you have any questions at all, I will see you tomorrow, or you can post in the comments field below and I may be able to answer them tonight. God bless you. Have a wonderful day. See you tomorrow.